Today we're going to look at an example of an airplane dropping some cargo, but this problem really is an example of any type of elevated horizontal launch. A B52 bomber moves horizontally at a constant velocity of 130 meters per second. The crew must hit a practice target located 623 meters away from where they released the bomb. Ignoring air resistance, determine A, the time it takes for the package to hit the ground, B, the altitude from which they should release the bomb, and C, its final velocity. Well, the first thing we want to do is draw an example of the diagram of what it looks like, okay? So we have our, let's see, we have a plane. All right, so we have a cargo of a bomber. It's going to drop this bomb right out of here. Okay, we know that it's moving with initial velocity of 130 meters per second. And so when this gets released or dropped, we're anticipating that it's going to fall, hit the target, and we know that the displacement in the horizontal, or the range, is 623 meters, right? Yeah, 623 meters from this initial launch point where it gets released and dropped. It's moving with initial velocity of 130 meters per second. Okay, filling in my variables, let's just go ahead and put them in. We have initial velocity, final velocity, acceleration, displacement, and time. Again, we're doing this for horizontal and vertical. Well, we know this is 130 meters per second. We can go right ahead and fill in our accelerations. We should know them by now. This is 0, and this is negative 9.8 meters per second squared in the vertical. The horizontal displacement is 623. Hope if I write the right number. And the time, we don't know, but we're going to actually solve for that first. We know that the initial vertical velocity is 0 meters per second. Okay, so let's solve for time. So where we're going to actually solve for time is going to be from the horizontal. I only know 2 of these at this point, so I need to solve for time in the horizontal. So we're going to use the displacement equation. All right, so we're going to use the displacement equation in the x direction. And by plugging in here, we find that 623 meters displacement is equal to 130 meters per second times t plus 1/2 at squared. Well, remember, the acceleration in the horizontal or x direction is 0. So this whole second half of the equation wipes away, and we're left with, as I said before, in the horizontal, we're only dealing with this equation that we need to worry about here. So the time is equal to 623 divided by 130 meters per second. Dividing it over, we find that the actual time in the air is 4.7923 seconds. Okay, so we're going to write that in here, 4.7923. That's going to be the same for both. Now enables me to find, and I have 3 variables in the vertical direction. Part B then asks, well, what is the altitude from which this bomb must be dropped? So if I look at this in the vertical displacement, this is the altitude. Okay, so we're going to solve for the altitude. Well, we're going to use the exact same equation just in the vertical. So let's go ahead and do that. Okay, so after we've identified and wrote our equation in variable form, solving for the altitude here, we're going to plug in. Well, the initial velocity in the vertical is 0 meters per second. So this first half goes away. We're left with plus 1/2 acceleration in the vertical, negative 9.8 meters per second squared, times the time squared. Plugging into our calculator, we find that the vertical displacement, or the altitude, is negative 112.5 meters, which is approximately negative 113 meters using 3 sig figs. So the actual altitude would be 113 meters is the altitude, because the way we reference altitude is height above the ground. But when we're tracking it using the kinematic equations, we know that the actual negative the displacement in the vertical is negative 112.5, because that's how far it actually fell, with the final position being at the ground. So the last part that we're asked to find is how fast is it moving? The actual velocity, right? So we're looking for the final velocity. Remember that velocity is going to include the magnitude of the speed, how fast it's moving, plus the direction that it's actually traveling at as it hits the ground. So magnitude and direction for velocity, because it's displacement, because it's a vector, that is. Let's go ahead and we need to find the final velocity. We know all 4 of the other variables. Remember that we're going to need the horizontal and the vertical components to find and combine to find the resultant velocity vector of how fast it's actually moving. So let's first solve for the vertical velocity. Okay, so we're using that first equation. Final velocity in the vertical is going to be equal to the initial velocity in the vertical plus the acceleration in the vertical times time. The initial vertical velocity being 0, we're only left with negative 9.8 meters per second squared times the time of 4.7923 seconds. Gives us a vertical final velocity of negative 46.964 meters per second, or using 3 significant figures, negative 47.0 meters per second. However, I'm not trying to round here. My final velocity, I want to hold on to this velocity here with the unrounding of sig figs. We plug that back into here, and now I need to find my resultant velocity vector. So again, if we're looking at the tip to tail method, I have my horizontal velocity of 130 meters per second, and I have negative 46.964 meters per second, and it's this resultant velocity vector here, v, that we're trying to solve for, and ultimately this angle here. So first, let's find the magnitude of v using Pythagorean's theorem. All right, so using Pythagorean's theorem, v squared, the resultant velocity vector, is going to be the square of the 2 components, the vertical and the horizontal. So it's v squared equals horizontal velocity squared plus the vertical component squared. Plugging them in, we find that it's 130 meters per second squared plus negative 46.946 meters per second squared. We're going to square root that entire sum to find v. And the velocity is 138.22 meters per second. That's how fast we are moving. But to define my velocity, I also need to find this angle, in which case we can use our trigonometry equations. And we know that we could use the sine, which would be the opposite over the hypotenuse. We could use cosine, which would be the adjacent over the hypotenuse. Or we can use tangent, which would be opposite over the adjacent. So since I'm given this factor here, these are both solved for, I'm just going to use the tangent function to find this angle, okay? Okay, so to find this angle, we know that the tangent of theta is going to be opposite over the adjacent. But I need to find the inverse tangent of that function to find the actual angle. So theta is equal to the inverse tangent of the opposite over the adjacent side of that right triangle. So plugging in, we find tan to the negative 1, or the inverse tangent or arctangent, is negative 46.964 divided by 130 will give me an angle of negative 19.863 degrees. So this right here is that 19.683 degrees. And the way that you would reference this as the complete velocity of the bomb as it's hitting the ground is that it's moving with a velocity of 138.22 meters per second at an angle of 19.863 degrees below the horizontal. So everything is in reference to the horizontal reference plane. So when you get a negative like this, because of the fact that the negative vertical velocity is telling you that the angle is below the horizontal reference, is how you would refer to that.